Much for making it today, especially on a Saturday morning. It's a pleasure to see everyone. My name is Teryn Johnson, as previously said, and I will be doing my talk today on bridging electrophysiological scales in a rat auditory paradigm. So this is a figure that I think I saw Dr. Terry Sajanowski hanging out around. He's probably intimately familiar with this, but I want to start with saying that the brain is an extremely complex and unique system that spans both vast spatial as well as temporal dimensions. From studying the quick events surrounding molecular binding to studying long-term memories, researchers analyze the brain on scales from fractions of milliseconds to years, potentially decades. On the spatial scale, researchers study molecules such as neurotransmitters that are nanometers in scale to the peripheral nervous system that spans meters. One added source of complexity in studying the brain is that these scales do not always co-vary with each other. For example, we often study memory not only on the macro scale with cognitive tests, but also on the micro scale in the changing of synaptic weights. The sheer level of complexity begs the collaboration of different specialized groups to be able to tackle some of the most important questions about how the brain fundamentally functions. Throughout the year, this diverse collaboration developed many different methods for studying the brain, these methods specializing in answering questions at different temporal and spatial scales. As shown in this figure, with spatial scale on the y-axis and temporal scale on the x-axis, different methods specialize in answering different questions. The issue, however, is that we know that many of these measurements that we take are highly correlated with each other, but the methods used to study the brain are often non-overlapping in scale and non-trivial to make the connections between them. Even when the methods do overlap to measure the brain at the same temporal and spatial scale, it can be quite challenging to perform both simultaneously. So for example, although EEG and MEG record the brain on the same temporal and spatial scale, measuring both simultaneously can be quite challenging. This often leads to comparisons between results from different subjects or even the same subject undergoing different measurements at different times. However, these strategies do not produce apples to apples comparisons and can lead to misunderstandings as to whether the two signals are actually co-occurring. To be able to truly bridge different measurements taken at different temporal and spatial scales, the same subject must be recorded at the same time to try to answer questions about how both signals might interact and be related. Making these connections are critical because it would allow researchers to bridge the knowledge gained from each method to obtain a more holistic understanding of brain dynamics. In this study, we attempt to connect two different electrophysiological recordings that span a large difference in spatial scale. EEG is typically used in humans and other larger mammals with a number of applications such as studying and diagnosing neural and psychological disorders, while as LFP is typically used in smaller animals to study fundamental mechanisms of local circuits. Fundamentally, how do these signals arise? Well, EEG tends to be a signal that is the summated currents from many different systems that have volume conducted to the scalp. LP tends to be viewed as a signal that is more local representation of the currents occurring in and around the system. There are a number of complexities that arise when trying to bridge these two scales, first of which being that the recordings are taking place at two different spatial locations, and many modern methods of recording EEG involve large numbers of electrodes arranged in a cap that covers the entire head, which would make it sometimes challenging to also record intracranial signals. Another main problem is that the summated signal of the EEG can look very different from any individual source signal, including that from the recorded LFP. Since the EEG is summated from many different signals, for example, A, B, and C, the EEG signal is going to have a combination of many different characteristics of those signals, such as is demonstrated to the right. There are also a number of factors that can cause the signals between the EEG and the LFP to differ. One such being that the LFP, like the EEG, can also be volume conducted from even distant systems and not always be representative of local processes. The degree of synchrony of neurons can also affect the response recorded. If many neurons are being engaged at any specific time, then the currents that they generate can potentially summate and generate a larger response in the local field potential that may or may not lead to a noticeable change in the EEG signal. Whether you see a consistent change between EEG and LFP signals can also be affected by the orientation of individual neurons, whether it be due to the system topology, such as the presence of sulci or gyri, or how the neurons' dendrites and axons are oriented, for example, whether they span multiple layers or reside within a single layer. For all these reasons, not all characteristics of the field potential in a local system are going to be represented in the EEG signal. It is the goal of the study, therefore, to isolate characteristics of the LFP signal that do covary with the EEG signal and use them for predicting the dynamics of the EEG signal. In this study, we recorded both EEG and LFP in primary auditory cortex of 6 rat subjects, 3 of which were male and 3 of which were female. A1 was chosen as a candidate system because it is a well-characterized system that has been shown to produce robust responses in both the EEG and LFP signals of not only rats, but other species such as humans as well. We implanted a 16-channel 5 mm silicon probe in 6 rats to record field potentials in primary auditory cortex with stereotactic coordinates detailed at the bottom left. And then contralaterally, we attached a skull screw to record EEG over primary auditory cortex using the same coordinates. In addition to this, in 4 of the later rats, we also attached a wire to an additional skull screw over frontal cortex. The stimulus for the study was chosen because it is easily repeatable and produces robust and reliable responses. It was critical because we wanted to ensure that the response generated in the rat was as consistent as possible for modeling purposes. Stimulus I'm going to focus on for this presentation is one designed to elicit an auditory stimulus response, steady state response. Each stimulus was presented at a tone of 2000 Hertz carrier frequency, but the timing of the presentation of the tone is modified to generate different rates of presentation. Pictured here are 30 Hertz, 40 Hertz, and 80 Hertz rates of tone presentation, but we also recorded using 20 and 50 Hertz stimulus as well. I'm going to play a very small snippet of these, but I was also told to warn people that it might be a little bit loud. I'm going to preempt this by turning the volume a little bit down, but if you're wearing headphones, this is your warning. Hopefully that wasn't too terrible. That was the 20 Hertz or the 30 Hertz stimulus. Let's listen to the 40 Hertz and how that differs.
Teryn, I'm not hearing them at all, so maybe you can turn the volume up a bit.
It might be possible that the Zoom is messing up, so I'm just going to skip it. Essentially, it just sounds like kind of clicking noises at different frequencies. Okay, so using the stimulus, what are some of the predictions that we can make of what we should see in the LFP and the EEG signals? First, previous studies have shown that the ASSR A1 is maximal for 40 Hertz. And second, the 80 Hertz ASR is believed to originate from the brainstem as opposed to locally within A1. So therefore, there might be fundamental characteristics of the LFP during this condition that might have different characteristics. It might be important for understanding what is actually being generated locally for the other conditions. So here are some results from our ASSR studies. Found here are the grand average results. To the left is the grand average across subjects, so all 6 rats, for ASSRs of 20, 30, 40, 50, and 80 Hertz. The thick black line corresponds to the recordings taken from the skull screw above contralateral auditory cortex. The thick green line corresponds to the recordings taken from the frontal EEG skull screw. And the thinner red and blue lines correspond with probe recordings, with the red colors corresponding to the most superficial positions on the probe, and the blue corresponding to the most deep positions on the probe. To the right is average results for each individual rat subject across multiple recording days. Note that subject 4 does not have an auditory EEG wire due to complications with the surgery. And also note that subject 5's probe eventually failed, so his recordings are somewhat limited. As you can see, there is a clear maximum at 40 Hertz ASSR for most subjects, consistent with our predictions. While there is a maximum at 40 Hertz, it is only fully significant across all signals when compared to the 80 Hertz condition. And when compared to 30 Hertz, only the frontal EEG as well as the most superficial probe channels came out as significant. 20 Hertz and 50 Hertz came out as insignificant. While it's encouraging that we are getting somewhat consistent results to what we would expect, our main goal and what we are beginning to explore is to find covariant feature of the LFP and EEG signals. Plotted here is an example of a single day's recording from one of our subjects. 3 cycle filtered averages of the LFP and EEG are shown with the same color scheme as the last slide, thick black line corresponding to the auditory EEG and red and blue corresponding to the LFPs. The top row has each signal plotted on top of each other to demonstrate the relative amplitude of the signals, and the bottom row has the field potentials spread out according to spatial locations compared to their relative phase. The columns correspond to different ASSR stimulus conditions, as shown at the top. One of the things that we're interested in exploring is the relationship of the phase of the field potentials with the strength of the ASSR. As you might be able to see here, one of our questions is if having out of phase potentials correlates with strength of the ASSR. This could potentially make sense as it would allow the current system 8 and allow the signal to reach the scalp without being as attenuated. Another question we have is that if the EEG and LFP amplitudes co-vary, as you can see here, however, the strength of the EEG signal does not seem to have a consistent relationship with LFP strength, at least in this particular day. In summary, we've seen initial results that have been consistent with some of our predictions going into the study. Specifically, we found that the response to the 40 hertz stimulus is maximal compared to other frequencies. And unexpectedly, the response to the 20 hertz and the 40 hertz 50 hertz were also high. There have been some past results that show that maybe the tuning curve for this for rats was slightly different from humans with a slight preference to 50 hertz. That's not exactly what we see because it's not in all subjects. It's only in some of the subjects that we recorded. While modeling is the next step for the ASSR data, other future directions include exploring data that we collected in conjunction with ASSR stimuli, specifically responses to a mismatch negativity response. Ultimately, we are very excited about the data and we were able to collect in addition to Archer's data that you saw just previously. Really want to thank the Kavli group for being able to make us collecting this data possible. In addition to that, I would like to thank some stellar people in my life, specifically my advisor, Dr. Lara Rangel, and Dr. Shauna Colson, who have been actively helping me with this project. In addition, very special thanks to Austin Gallagher, who was a research assistant in our lab that was critical in collecting pretty much most of the data, if not all of it. My advisors, other advisors, Dr. Andrew Shiba, Dr. Ron Mukmel, Dr. Douglas Nitz, Dr. Todd Coleman, and two of our lab members, specifically Mia Borzella and Pam Riviere, that have been also very helpful in collecting and making sure that data collection went very smooth. Thank you very much. I look forward to your questions.
Great, thanks, Teryn. Another great talk. We have a few minutes for questions. I don't see any in the chat, so I'll